Yeah. All right. Thank you very much, Professor Shah. And also, I want to thank the organizers of the Prairie Analysis Seminar for giving me this opportunity to present this talk. This is a joint work with my advisor, Professor Atanas Stefanov. He moved to University of Alabama recently. All right, so this is the outline of my talk. I hope I will be able to minutes. So I will give some introduction. My approach is using this of variation. That is how we will construct the wave. And then we will also try to study the linearized problem, and then taking advantage of the linearized problem to study the stability, in fact, the spectral and orbital stability of this wave. So the equation in mind is the fractional NLS. So with the nonlinearity concentrated at a point, in this case at the origin, 0, and with the initial data. Now, this equation has some physical application. The famous one, I guess, is it actually model a small spatial region, the charge accumulation in a semiconductor interface. And more interestingly is the steady states of the solution is the one that
delta 0 is the direct mass.
Yes.
Yes.
Yes, it is the direct mass. Yes.
Okay, I see. That's very formidable. Yeah. So when people see direct mass, okay. Yeah.
Right. And
continue.
Yeah, and also,
Abba, yeah.
Okay. Yeah. And also, like, even the notion of solution, it has to be in weak sense and all that because of the direct mass, right? You have to really the solution is an integral form. Is right. So then if we take this answer and we plug it into the Schrodinger equation, we will have the profile equation, also again in the weak sense because of the track mass. And now the goal is to exist solutions, and moreover to see if these constructed waves are stable. Now, this has been done for s equals to 1 and n equals to 3 by Adami and Noger and their respective collaborators. Later, they also study the case when n equals to 2. In our work, we study any dimension. Of course, we have to be careful with the sum-level embeddings. So for that, we will have an extra restrictions on n, but not just 1 and 2. So the first exist. So by trying to, and so these are the Pukuchev identities. And from this Pukuchev identity, we see that, well, at least from equation 1.3, we expect positivity on both sides for this identity to hold. So that means we want this guy to be positive. And then that means either SW are positive and the numerator is also positive, or they are both negative, right?
Abba,
negative.
Abba,
Yes.
Can you turn off your video so that you have a better internet connection, because you sometimes there is a pause during your talk.
Okay.
Turn off your video and only show your screen.
Okay. How about now?
Yeah, that's better.
Okay, thank you. So then looking at the Pukuchev identity, I expect, right, this is squared, so this is squared, so this better be positive. And then that gives us some sense on the range at which this wave will exist. So that is the corollary. It's either both omega is negative, S is less than n over 2, or omega is positive, S is bigger than n over 2, but then the positive one is the one that is more physical. So, and if S is bigger than n over 2, we have the Sobolev embedding. So actually the constructed waves are continuous, automatically continuous. And I will talk more on this embedding because we end up showing the exact constant for this formula for it in the Fourier transform. So then how do we wave? Well, we try to approximate the delta function by, say, the Gaussian, right? Like a function that have weight 1 and then so this is we approximate the delta where we this minimization problem. Of course, that depends on n, and the goal is if we take n to infinity, we should recover the original problem. And then we try to study the, as I said, we try to minimize this functional. We end up showing that this unconstrained minimization problem actually have solutions that are bell-shaped, and not only that, the equation again in the distribution sense. Now, one will hope once we take the limit as n goes to infinity, right? This will produce the original wave that we intend to study. And to do that, we showed that this minimization, Mn, right, this guy is actually bounded above and below by a constant that does not depend on n. Furthermore, we actually show that these sequences are pre-compact. So then in that case, we take a limit, and once we take the our initial solutions. But doing this minimization problem, we realize actually maybe we can get the exact constant for this Sobolev. So we study this functional where we put the L infinity norm in the denominator. And then now we study the corresponding minimization problem. That is, we try to minimize J, this unconstrained. And then for now, let's just donate the infimum of this minimizer when we restrict it to the Schwarz class as C squared omega. And we end up showing actually this is the exact constant of this Sobolev embedding. Most probably this has been done somewhere else, but this turned out to be related to our work. So we said, why not explore it? So of course, for the Sobolev constant, we end up, okay, let's define this triple norm as the normal weighted L, right? Sorry, HS norm here with omega. And then the goal is to realize what this C omega, and we can define it as the supremum over C such that this Sobolev embedding works. And without loss of generality, actually we can replace the L infinity norm with the value at C0, especially in our case, since we have bell-shaped rearrangement, so the maximum is at 0. So again, we write C squared omega to be this, right? And then we end up showing, again, for S bigger than n over 2 omega positive, like the range at which the wave exists, some slight gamma that is minimum between 1 and this S minus n over 2. This C squared is bounded by our minimizer, and which is also bounded by, again, C squared plus C over n. So taking n to infinity, we know where this goes to. We already showed what it is. And then we actually recover that C squared is actually Mn at the limit. And that is how we end up writing out the formula for the sharp Sobolev constant. Right, and this is what I'm saying then. For this range, after taking the limit, actually C squared is this formula, right? So this is like the Fourier transform of the H's. But then this is, we have the exact constant, like the formula for the exact constant. And for our original wave, we can write it in this form. So this is the solution of the original wave we tried to study. We have the formula for it. And now the goal is to do stability. And for stability, we need to linearize our problem. But then once you linearize, you have an operator that you need to make sense of the domain. So this actually, we use the idea by Adami and the collaborators where they define the domains this way. So first of all, we look at the green function of this Schrodinger operator or fractional Schrodinger operator. And then if we take the Fourier transform, we can solve for GS that depends on lambda as such. And then since S is bigger than N over 2, this GS is actually in HS, which from the Sobolev embedding is they are continuous. And then if we define the domain of these LC operators as such, this is the idea by Adami, I repeat again. And then, of course, I have to write what the action is. The action is, if you give me LC phi, it will produce this, right? And if you rearrange, you see that we are getting the operator that we intended to study in the first place. So with this definition, we can now go ahead and linearize.
So, Abba,
yes.
So right now you're using the variational analysis to approach this problem. The reason is because, I mean, in this physical space context, you turn the delta mass into a function value.
Yes. Yes.
So that's very easy for you to deal with.
Yes, of course. Of course, because I don't want to deal with the delta mass that in the, because the moment I deal with the delta mass, I will not see the futures. It will just become like a scale, like the scalar. It will just be like the Laplacian plus delta plus some scalar function from some scalar. And in that case, I will not be able to see all these physical properties, and I might lose some stability argument there. So that is why we approximate first, construct wave that way, and then we later take the limit.
What do you mean approximate?
Right, what I mean by approximate is right here. Right here. So I approximate the delta function by Gaussian type functions that when I take the limit, they convert to the value at 0, which later produce it looks like the delta function at the integral, right?
Okay,
you see what I'm saying?
Yeah,
right.
I kind of, okay. Continue.
Yeah, okay. Right, and then, as I said, the next thing is, okay, if I take the perturb to the NLS, the fractional NLS, I can linearize it in this way, right? So I have L plus and L minus defined as such, and my J to be this L also arranged in L plus L minus. Now the goal is to do spectral stability and orbital stability. So I need to have the eigenvalue setting. And for that is, after doing this assignment, I have the JLV equals to lambda V. And now the whole problem is I need to know the spectrum of JL. because the spectrum of JL will lead to stability. And in fact, we use the Hamiltonian index theorem to study this. Of course, first of all, we need to actually make sure that this operator L, C here, the reason why I say C because it can be plus or minus, they are self-adjoint. So that is the first thing we actually showed that these operators are self-adjoint, and not only that, they have this spectral property. If mu, right, this mu here is bigger than the sharp, then this operator L mu has exactly one negative eigenvalue, meaning it has most index 1. And this is one of the properties we need for spectral stability. And if mu is exactly at the Sobolev constant, then we have 0 is a simple eigenvalue. So this is like L minus, and there is also a spectral gap. And what you expect is if I am less, then I just have a simple eigenvalue, one positive, and then I also have the spectral gap. So 2 for stability and the last one for instability. So then if I apply this to L plus L minus, because that's the one I have in mind, then L minus for L minus 0 is a simple eigenvalue with eigenfunction coming from the Green function of the fractional Laplacian. Moreover, I have the spectral gap, right? So that is if I restrict this to the eigenfunction, the orthogonal of the eigenfunction, I see that L minus is positive. And then for L plus, it has exactly one negative with eigenvalue phi 0. And if I restrict the operator to the orthogonal of this phi 0, I see I have a spectral gap. So this, together with the instability index counting theory, or the Hamiltonian index counting theory, what some people call it, we can see that, well, so J star, remember what J star is. This is J star. 1. So then J star has this property, right? J star is minus J, and which is J inverse. And also, I need to know the number of negative eigenvalue for this operator L. Right here, for this operator L, because I will use this too. So for that, I know L minus have 0 negative eigenvalue from this, L plus has 1. So L negative eigenvalue. And for the kernel of L is the kernel of L minus and the kernel of L plus. L minus have the phi as its kernel, L plus have 0 in the kernel. So then the kernel of L is exactly this. How am I doing with time, Professor Shao? Do I still have some time?
Continue.
Huh?
Continue. You have enough time.
Okay, thank you. So then it boils down to calculating for the spectral stability, is boiled down to calculating the so-called Vaitov-Kolokov condition, meaning I need L plus inverse phi to be less than 0. And this we actually, since we know this Green function, it boils down to calculating this. And this we calculated using the complex contour integral, actually. Because we are interested in the sign. So the sign of this is equals to the sign of this, and this we end up showing is equals to the sign of this. This equality right here is where we use the complex contour integral, which in the paper we have it in the appendix of the paper. So then we show then this is actually spectrally suitable if and only if sigma is within this range. And if you take n equals to 2 and s equals to 3, you recover the result by the previous publishers. S equals to 1, n equals to 2 and 3, we can recover their result. So this is spectral stability. Now, the goal is we also want to show orbital stability, but for that, we need this, which we already proved, but we also need L plus to be coercive. In other words, if I take anything orthogonal to the standing wave, L field of that should be positive. Or there should be a delta such that this inequality existed. So we also established this. And of course, to do orbital stability, we expect it to be within the range that I have spectral stability. And we add extra assumptions. So this is a conditional orbital stability because we assume dependency of initial data and global existence. So with these two assumptions, which at this level we just take an assumption, of course, we also assume the conservation of mass and Hamiltonian. All this, at least for n bigger than 3, is an assumption. For n equals to 3 and 2, this paper by Adami, they actually showed they have conservation and they have global existence. But for our case, we assume that and then have a conditional orbital stability, that the moment these assumptions are satisfied, then this
So
will
Abba,
yes.
what's the structure of the equation that make you to make these assumptions?
You mean, so the question, let me go
Maybe
back to
those parts you don't like it, then you make these assumptions and
no, it's not because
no?
I don't like it. Like it is because for me to show orbital stability, I need global existence. And I don't have global existence. So that's why I assume it for, so then this becomes conditional orbital stability until the global existence is satisfied. If whenever it's proved, then I have stability. I don't like it, of course, because I don't have it. This is the equation.
Yeah, but okay, continue, yeah.
So this is the equation that if I have global, and we actually expect to have global existence. It's a conjecture. We don't say we have it, but we expect to have global existence in this range as bigger than n/2. This is a conjecture. We did not prove it. We said within this range, the equation should be global. We did not prove it. Maybe something to do, but that is not the direction we took. We are stability, orbital stability. So we could have stopped right here and said, well, we have stability, happy. That way we don't need to deal with global existence, or we add assumption of global to orbital stability. And these are the references we used. So these papers work 2D, 2-dimension, and then we work with any dimension. Yep. And thank you.